Welcome to Lecture 4 of Embedded Systems, in which we shall continue our discussion on the input-output ports, and once done, we shall move on to describe the branches and the branches instruction in this cortex-m assembly language. And we shall conclude our lecture with the introductory discussion on the SysTick Timer. In continuation of our discussion regarding the LED interfaces, there is an important precaution, which is that your microcontroller can only output limited amount of current driving the peripherals such as LEDs, switches, and others. And there's also some limitation on the amount of current entering the microcontroller. We call it sinking the current. At this point, I don't know the exact value, but it might be helpful to consult the relevant data sheet. So if there is an upper limit on the amount of current entering or leaving the microcontroller, then we must be careful in interfacing the peripherals. For instance, if we are connecting too many LEDs or few LEDs needing current that accumulates higher than 12 milliamps. And if those LEDs are connected directly to the microcontroller, that may result in damaging the microcontroller. So they must not be directly connected to the port pins. Instead, we shall insert buffers that can sink that higher amount of current, such as ULN 2003 7405 or 7406 or 7407, between the microcontroller and the LED when we wish to interface the peripherals. And let's take a look with the help of an example. On the left hand side, we have an LED connected to the port pin that requires just 2 milliamps. In that case, we can directly connect that LED to the port pins. Imagine that this is the only LED that we are going to connect to the system. Therefore, we connect this LED directly to the port pin by means of a resistance here. And the resistance is going to obviously limit the current and also make sure that the LED turns on with adequate brightness. So if the requirement is 2 milliamps for an LED to lit up the LED, then we can do some simple calculation to find out the values of these resistances. In this case, we are saying that the LED is directly connected to the microcontroller. The only component that is between the port pin and the LED is the resistance. So there is a direct connection. So direct connection between the LED and the microcontroller. That is when we want to drive the LED in the positive logic, meaning that the LED must be turned on when the output is high. And if we want to turn the LED on when the output is low, then we may wish to modify our circuit slightly. So in this case, the positive supply voltage 3.3 volts is connected to the resistance, and which in turn is connected to the LED, whose other terminal is connected to the microcontroller port pin. So that when the output goes low, the current, the cathode of the LED is connected to the low voltage, and the anode is connected to the high voltage 3.3 volts over here. And then the current can flow through the LED, but we must be careful and insert an appropriate resistance as we did here in case of positive logic. Nevertheless, in both cases, the LED was directly connected to the microcontroller. That's how we say it. This is very different from a situation when the LED demands a current which is higher. So imagine that the current is close to 10 milliamps, such as 10 milliamps. So we might be careful and not to connect LED directly to the microcontroller. Instead, we are going to use buffer. So in case of positive logic control of the LED, we may want to use buffers such as 7405 or 7406 or ULN 2003V. And the way it works is that when a microcontroller outputs high voltage, it sets the output of the buffer to the low voltage so that the current can flow through the LED. But the current will not enter the microcontroller. Instead, the current goes to the ground through the buffer. So the only job of the microcontroller is to set the voltage level at the input of the buffer. That's it. There is no high current that is flowing to the microcontroller. In fact, the buffer is carrying all the current. Likewise, in case of negative logic, if there is a danger of sinking higher amount of current, a large amount of current, then again we can use 7407 microcontroller. And because we are working with negative logic, so we want LED to turn on when the output of the pin is low. So 7407 outputs low voltage when the input is low. And if the input is high, by the way, the output is high impedance state. That is, this connection, this output is at high impedance, meaning that there's a very high resistance. Essentially, this is an open circuit situation, and therefore there is no current that can flow through the LED. So that's in case of high voltage. But if the input is low, then the output is low, and then you can see that the current enters LED, and then it sinks to the ground through the buffer. Remember, the output of the 7405 and 7406 is at high impedance state C when the input is low. Next, switch interfacing. We describe how to interface switches to the microcontroller, and we looked at examples where the switches were connected through external resistances to the microcontroller. So there were external resistances in our last lecture, and again here the two examples, the positive logic and the negative logic switch interface. We see that we have external resistance of 10 kilo ohms here and also 10 kilo ohms over here. The only difference between this circuit and the one below here is that the upper circuit works with positive logic. The lower circuit works with the negative logic. But in both cases, we have external resistance to limit the amount of current entering the microcontroller. So again, if we take some notes, we can say that to limit the current of microcontroller. There is, however, another way to limit the current without using external resistances. We can activate internal resistances. Internal resistance. Okay. The two examples on the right hand side of the table describe how to activate the internal resistances. In the first case, the positive logic switch interface, the switch is directly connected to the port pin, such as pin number 4 of port A. There is a switch that can connect pin number 4 port A to 3.3 volt, or it can disconnect or it can produce a disconnection between the positive supply voltage and the pin number 4 port A. But whenever the switch turns on, then there's a danger of excessive current entering microcontroller, because we haven't attached any external resistance. So note that there is no external resistance here. However, there is an internal resistance, and that is set by setting certain bits of the port configuration registers that I'm going to describe shortly. But once the internal resistance is activated, then we are safe. We have essentially limited the current of the microcontroller. And these are designed to work with 3.3 volts, I believe, or maybe up to 5 volts, but not higher than that. In case of negative logic, again, we are going to activate the internal resistance by setting the bits of certain registers, port configuration register. So in this case, the 3.3 volts will be supplying the current that the current flowing through the 3.3 volt power supply will be limited by this internal resistance. Once the switch is turned on and the switch is essentially short circuiting the port pin to the ground, so this resistance is going to limit the current. But the difference between the two circuits on the right hand side is that in the first case, the internal resistance is the pull down resistance because it is pulling the pin here, port pin, to 0 volts when the switch, sorry about that, when the switch is open. So when the switch is open, such as shown here, then to make sure that the voltage at the pin is 0 volt, it is grounded, we have the pull down resistance. That's why the resistance in this case is pull down, PD, pull down resistance. In the other case, however, if the switch is open, then by means of this resistance, the pin PA6, the pin number 6 of port A, will be short circuited to the supply voltage because there is no current that is flowing through the pull up resistance. So we call this resistance pull up resistance. And one of the things to note is that if so you either activate PDN or PUN. If one is activated, then the two cannot be simultaneously activated. So either pull down resistance or pull up resistance, but not both. Because in that case, we might be running the risk of enabling large amount of current to the microcontroller. And also, but more importantly, the logic level at the pin might be ambiguous. All right, so how can we enable the pull down or pull up resistance? We have port configuration register, GPIO, port X, PDN_R. That's the pull down enable. We can just say it's a pull down enable register. We are interested in only the lower 8 bits of this register and the one after that, that is the pull up enable register. Pull up enable register. Only lower 8 bits are required to be set or reset, and we're going to set basically, meaning that, for example, in the first case, if we are interested in enabling the pull down resistance corresponding to pin number 4 on port A, over here, pin number 4 port A, if we are interested in activating the pull down resistance, then we are going to set the 4th bit of the pull down enable register. In the other example, we are interested in enabling the pull up resistance on pin 6 of port A. For that, just set bit 6 of the pull up resistance, pull up enable register of port A. Activating pull up and pull down resistances provide a safe way to interface particularly switches. Next, whenever we are interfacing switches, mechanical switches, with the microcontroller, we should always remember that mechanical switches may oscillate between on and off state due to their inertia, friction, mass, spring, and other mechanical properties. In that case, it is better if we wait for some time, typically ranging up to 10 milliseconds, before reading the data from the port where the switch is interfaced. And there are several ways to introduce delays. We saw that in the last lecture, and we shall see that again with the help with a new module that we haven't yet discussed. That is a timer. But in the meantime, please look at figure 4.24 of textbook number 1, in which there's a flow chart that implements a pseudocode to read the status of the switch, the logic level at the switch. And it does that by introducing 10 millisecond delays. It's not a complicated program, very simple, and hopefully you can follow that easily. We're now going to move on to describe the syntax of the conditional branch instruction. For that, it is important to recall the role of suffix we appended after the arithmetic, logical, or shift or rotate instructions. To help you recall, I give you an examples. The example of the AND instruction with the suffix S. And we said in lecture 2 that when the suffix S is there, it means that in addition to performing the normal bitwise AND operation, we're also going to the microcontroller is also going to update the code bits. In this case, it is going to update only 2 code bits, the N and Z, the negative result code bit and the 0 result code bit described in the last lecture. Another example is that of logical shift right with suffix S, performing logical shift right operation, but also updating the code bits, 3 of them in this case, N, Z, and C, because the carry, the bit that is shifted out, goes into the carry bit. And finally, the add S instruction performs the addition on the registers and also updates the code bits. In this case, all 4 code bits may be changed after the execution of this instruction. So why is that discussion important? Because based upon the value of the code bits, we are going to dictate the course of the execution of our program. To describe that and to be able to understand in more detail, let us look at some examples. The check of equality. When we wish to perform the equality check, we may be interested. We can just say that check the status of the 0 flag, because the previous instruction, which may have compared the 2 numbers, and if those 2 numbers were equal, then that instruction must have set 0 flag to 1. I'm using the word flag and the code bits interchangeably, so we can also say the code bit or the flags. These are just synonymous. The code bit or the flag are just synonymous. So anyway, so Z code bit or the Z flag set equals to 1. That is a signature of the equality check. Not equal, unequal. Z flag equals to 0. Similarly, what about the the perspective of our discussion is that we are sort of comparing 2 numbers. Just imagine, for the sake of understanding as well, so comparing 2 numbers. They are going to be stored somewhere in the microcontroller, but such as one of them may be in register, the other one is just some operand 2, which can be a register, which can be a constant. It can be a constant as well, or a register. Anyway, so we're comparing 2 numbers. We don't care where they are. For the moment, we can just think of the contents of the registers as two numbers, then for example, in case of noting that if one number is higher or it is higher than or equal to the other number, when the two numbers are unsigned, then the carry bit should be equal to 1. Carry bits is equal to 0 when one number is lower than the other number. That's unsigned comparison. So again, the emphasis is on the comparison. Negative bit is set equal to 1 when the number that one number compared to the other is less than, that's negative. If n is 0, then the comparison answer was either positive or 0. Overflow, v equals to 1, no overflow, v equals to 0. And the list goes on. And one of the things to note is that sometimes it is important for the signed comparison. That's where we use less than or greater than, or less than or equal to, or greater than or equal to. So these four instructions are used whenever the signed comparison is required. So what do we gain from this discussion is that whenever we are going to compare two numbers and to be able to make decisions based upon the answer, decision depending upon the answers of the comparison, then we are always going to look at some of these code bits or the flags. And remember, again, we are going to work with the four code bits: the overflow, 0, negative, and carry. Now let us look at some of the examples. Let us try to parse a simple conditional branch instruction example, the branch if equal. In this case, the instruction should be read as follows: BEQ, branch if equal. EQ is actually a suffix, and we saw in the last slide that EQ suffix corresponds to the 0 flag, and it checks if 0 flag is equal to 1. The other part of the instruction is the branch, B for branch, which in simple English means go to. Go to the instruction whose label is some instruction label. So what we're really saying over here is that check if 0 flag equals to 1. If so, then go to the instruction whose label is some instruction label. The conditional branch instruction often precedes the compare instruction. The syntax is CMP, followed by the registers or constants. In this case, we are going to compare R0 with R1. The compare instruction only performs a subtraction operation, except that the result of subtraction is not stored in either register or the operands. However, what it does is that it only updates the code bits, set or reset. So it is only going to update the code bits. That's what it does. So compare instruction only updates the code bits, and those code bits are used in the following conditional branch instruction. An example we saw in the last slide, BEQ. It is going to check the Z code bit or the Z flag and jumps to some instruction whose label is some instruction label if Z flag is equal to 1. We have different types of branch instructions, and the syntax is given. The first one is branch if equal, and then the target. It says that if the previous comparison, if the two numbers were equal in comparison. And where do we compare? We are going to there is going to be some instruction over here. So there will be an instruction like CMP, let's say two registers R0, R1, and then we say BEQ target. So this CMP instruction, the syntax will be described later. So this is going to affect the code bits N, Z, C, and V. So based upon their values, the BEQ instruction will be executed. In this case, we are testing the equality, signed or unsigned. So basically, we are looking for the Z flag. And the target, what is this target? Target is actually a label of some instruction. So we are really instructing our microcontroller to jump. Branch means jump. So we say that jump to, so if R0 is equal to R1, so I think it is already given over here. So we compare R0 with R1, for example. And if R0 is equals to R1, then we are going to go to the target. Forget about this one. Let's say this is BEQ. So if R0 is less than R1, go to the target. Otherwise, just proceed to if R0 equals to R1, and if R0 is not equal to R1, just proceed to the next instruction. And this is how the flow works. The example actually given in the slide is that of the BLO, the branch if unsigned less than. And you can consult the previous slide to see what flags, what code bits it is going to check. Anyways, so if R0 is less than R1 in signed sense, then we are going to jump to the instruction whose label is the target. If not, then just simply proceed to the next instruction in the sequence. And likewise, we have branch if less than or equal to in unsigned sense, branch if unsigned greater than or equal to in the signed sense, and the branch if unsigned higher than. Similarly, we have conditional branches, conditional branch instruction when the comparison is performed in the signed sense. So branch less than, branch greater than or equal to, and branch greater than, and branch less than or equal to. And again, these instruction, the branch instruction can follow the sub instruction setting the code bits or the compare instruction. An example over here is that if you perform a comparison between register R0 and R1, and if in the sign sense R0 is less than R1, go to the target instruction. Otherwise, just proceed to the next instruction. And it will be further clarified with the help of examples later. Some simple examples highlighting the role of the branch instruction. The first one being the equality test code. So there is a number with a variable name G stored somewhere in the memory. We're going to load its address in R2, as we've seen several times before, and then we are going to invoke the index addressing to store the number, the actual number, into R0, and then we are going to compare R0 with 7. That is the same as asking the question, is G equals to 7? If they're not equal, then it says that go to the instruction whose label is next one. Right now here we haven't shown what is the instruction corresponding to the label next one, but assuming there will be some instruction, And if they are equal, now if G is actually equals to 7, if this condition is true, then it means that G is equal to 7. They are not, G and 7 are not unequal. So we are going to skip this instruction and we are going to come down to this instruction. And this instruction is BL. This is, remember, this is unconditional branch. So this is unconditional. Unconditional branch. So it is not going to look at the values of the code. It doesn't care about the code bit. It doesn't care about code bits. It is not going to care about the code bits. That is this instruction. It will simply jump to some instruction with label G equals 7. And that might correspond to a routine that may be utilizing this result to execute some code section for the given application. All right, in the next example, we have the inequality test. That is when we are interested in comparing G not equals to 7. So we say that again we are going to load the value of G into R0 and then we are going to compare R0 with 7. We are asking if G is not equal to 7. So in this case we are saying if G is equal to 7, then we are just going to jump to next 2. And if G is not equal to 7, then this instruction will not be executed and we arrive at this instruction. Again, this is an unconditional branch. Now let us look at some examples of unsigned conditional jumps. Comparing G greater than 7, and again G is some number stored in the memory which has been referenced and the value of whose value is now in R0. So R0 compared with 7, if G is less than 7, go to next one, the instruction at next one. If not, then we are going to skip. We are going to skip. We are not going to go to next one. We come here. And similarly, if we want to compare G greater than or equal to 7, then BLO. That is, if G is less than or equal to G is less than 7. So really over here we are checking if G is less than 7, then go to next 2. Otherwise, if G is equal to 7, then go to an instruction whose label is G greater than or equal to 7. G less than 7. A common technique that you may have learned by now is that we check the complementary condition. So if we want our program to jump to G less than or equal to 7 to the label G less than 7, then the conditional branch instruction after the comparison is the complementary condition to what we are looking for. So we say that if G is higher than or equal to 7, go to next 3. If G is less than 7, come over here. And finally, if we're checking if G is less than or equal to 7, then the complementary condition is that if G is greater than 7. Again, all of these comparisons are performed in the signed sense, given the conditional branch instruction that we are using. If G is less than or equal to if G less than or equal to 7, in that case we come over here and execute branch and link G less than or equal to 7. And in case of signed conditional branches, again we are going to replace the unsigned branch instruction with the signed branch instruction. So BLE, BLT, BGE, and BGT, and everything else remains the same. So far, the way we have used the conditional branch instruction was analogous to the if statement in the high-level language, such as Python or C. Now we look at a scenario where we are interested in implementing a structure which is similar to the if-else statement. For example, we wish to compare the two numbers. If G1 is greater than G2, then execute this block that is greater. There's some code that we don't care about. And then if G1 is less than or equal to, so you can consider the condition on the right hand side as the if condition, and the condition on the left hand side is as the else condition. So in that case, we're going to execute a different block. To some extent, the same flavor was present in the previous situation, but it is much more explicit over here. All right, so the two numbers G1 and G2 are in the memory. They are loaded into the registers R0 and R1, and then we are going to compare R0 with R1. And if G1 is greater than G2, then we are going to, so this instruction, the branch instruction, is going to take us to the instruction whose label is high. That's where the block of instruction is placed, starting. So the is greater is the block. Obviously, it is a label. It is a label of a set. Is a label of instruction. Is the label of, maybe I should say, label of the first instruction. Is the label of first instruction of the code of the code block is greater. And likewise, is less than or equal to is the label of the instruction of the code block of the first instruction of the code block is less than or equal. And we don't care what is inside the code block shown by the squares over here. But the only purpose was to make sure that we understand how the if-else structure is implemented in the assembly language.
Among best uses of the conditional branch instruction lies the implementation of the while loops and the for loops. We're going to first look at the while loop implementation, whose pseudocode is shown here. Essentially, we are going to condition the execution of the while loop based upon the comparison of the two numbers, G2 and G1. They are stored in the memory. We can only compare the two numbers when they are brought into the registers of the microprocessor. Therefore, we are going to load G1 and G2 into registers R0 and R1 in a way that R0 carries G2 and R1 carries G1. And then we compare the compare instruction R0, R1, and the remainder of the program execution is dependent on the result of this comparison. Back to the pseudocode of the while loop. If G2 is greater than G1, then we are going to enter the body of the loop. That is the body of the loop. And once the execution of the body is complete, we go back to check again if the while loop condition is true or false. Each time the while loop condition, as long as the condition of the while loop remains true, that is the true condition of the while loop. As long as G2 remains greater than G1, we keep on executing the body and return to check the condition again. If, however, the condition is false, the false condition, we exit the while loop and we proceed to execute the part of the code that is to be executed after exiting the while loop. In this case, we are going to execute next the program whose first instruction, the section of the program whose first instruction has a label next. So we perform a comparison over here between R0 and R1, and then we check BLS, the conditional branch instruction BLS. That is to say, if R0 is less than or equal to R1. What is R0 containing? R0 contains G2 and R1 contains G1. Therefore, we are actually comparing G1 with G2 by comparing R0 with R1. And if R0 is less than R1, then the false condition will assert the program to jump to the next instruction, the instruction whose label is next. That is, it comes over here. If, however, this condition is not true, that is, R0 is greater than R1, which means that G0 is greater than G1. Then we enter the body of the loop with the branch and link instruction. Now this is important because BL ensures that once the body of loop is executed, is completely executed, is finished execution, return. You need to return to the next instruction, which is here, B loop. We return. And once this instruction is executed, that is an unconditional branch. Simple B is, remember, unconditional branch. It is unconditional branch. It says that jump to the instruction whose label is loop. So we go back to the beginning of the loop, and we are going to reload the value of these variables G2 and G1 into the registers R0 and R1 respectively, and then repeat the whole process. And this is how the while loop has been implemented. Likewise, we can also implement for loops with the help of conditional branch instruction. Two types of for loops can be used: the ascending for loop and descending for loop. In the ascending for loop, we have a loop variable as used in the high-level language, such as I, initialized with 0, and we increment I. And in each iteration, we execute the body of the for loop that implements some function such as process. And the loop will run 100 iterations. That is when I exceeds 99 and becomes equal to 100, and this condition becomes false. So there are four components of the for loop here: the initialization, the conditional check, the increment, and execution of the loop body, that is process. The descending for loop works the same way, except that the variable is decremented, and the condition often checks if I is higher than 0. Therefore, the two for loops are essentially equivalent. And now we are going to look at the corresponding assembly code to implement the for loop using the conditional branch instruction. For example, if we are interested in implementing the ascending for loop, we initialize a variable such as I with 0. In that case, because the value is known, this constant, we can directly store this value directly into the register R4. So essentially, that I variable corresponds to register R4. And then we are going to compare R4 with 100 and see if it is higher than or equal to, if R4 is, so this, let me write it over here. So we're really checking if R4 is greater than or equal to 100. If that is the case, then this will force, if this condition is true, then we jump to the done and then proceed therefrom. We are not going to execute the process of the blue body. That's not executed. Now, if, however, this condition is false, that is R4 is not higher than 100, that is R4 is less than 100, then we go to the next instruction and execute the subroutine or routine or subroutine. Let's just call this routine. We don't need to use subroutine here. So routine process. We jump to an instruction that is going to be the first instruction of the routine, and the label of the instruction is process. And we are going to, after executing the process, we are going to return. That's why this BL is used for. We are going to return after executing the process, wherever that process is written. Once the instruction has been executed and the last instruction is probably going to be BXLR, that is going to bring us to the instruction next to the BL process, and that is going to increment the loop variable. This comment really says that we are incrementing the loop variable I equals to I plus 1. It's just that I is in the register. It has been placed directly into the register. And once incremented, we go back to the loop. Once again, this simple B is unconditional branch. Important to understand the role, the synergetic integration of conditional and unconditional branches. So this is again unconditional branch B. This is how you implement a count up for loop. On the other hand, if we are interested in implementing the descending for loop, we are going to initialize the loop variable I, which is in R4. So initialize I with 100. And then we are going to execute the body of the loop first. So it says that go and execute the body of the loop, which is actually the process, and then return to the next instruction. That is going to decrement the loop variable. That is I equals to I minus 1. And then the check condition B and E. Remember, we are not, so we haven't used any compare instruction over here. We haven't. And what is the reason? Well, because we already have the sub instruction that is decrementing, and the sub instruction also, so remember, sub S also affect the chord bits, just as the compare instruction affects the chord bits. So far, all of our examples have been utilizing the compare instruction, but the same effect can be achieved with the sub instruction, and that is usually preferred if sub is inevitable, is inevitably appearing in our assembly code. So we don't need separate compare instruction. We can just utilize the result of sub instruction. So sub instruction is going to decrement the register content values. R4 equals to R4 minus 1. In fact, R4 assigned R4 minus 1. And then B and E, branch if not equal. So it is going to check 0 flag, meaning that as long as R4 is not equal to 0, that is, it is higher than 0. So as long as R4 is greater than 0, meaning I greater than 0, keep on executing this instruction. It is going to, it is going to go back to this loop. And once R4 becomes 0, I equals to 0, then we are done. And then we proceed to the instruction whose label is done, and from there onwards. This is an example of a countdown or descending loop. Moving on to the SysTick Timer module. It is a module that is very similar to the counter
that you design in your digital logic design course. Timer works the same way. SysTick Timer is a 24-bit down counter, so it decrements its value at the bus clock frequency. And if we're using 80 megahertz bus clock using the internal PLL, whose discussion will come at some point later in this course, then the time period is 12.5 nanosecond, which means that the clock rising edge occurs after every 12.5 nanoseconds, and that's when the timer decrements its value. The value of the timer, the initial value, this n, will be some non-zero value, which will gradually decrement to 0. Initially, we are going to load or reload the timer with some value n, and it is going to decrement n to n minus 1 in the next clock cycle, then n minus 2, then n minus 3, and so on, up to 0. This is how the timer works. And at any point, you can read the value of the timer. When you load the value n into the timer, it is essentially a modulo n plus 1 counter, meaning that it is going to count the content, the contents, the current value will be modulo n. That is, it will be less than or equal to n. So the current value will be less than n. Maybe I should say, so the current, the value of the timer, so the at any point timer value is less than n plus 1. So for example, if we set n equals to 16, the value n equals to 15, then the value of the timer at any stage is less than 16. Now, in order to be able to use the timer module, similar to the case of I/O ports configuration registers, we have the timer configuration register, NVIC, SysTick Timer, which are memory mapped, meaning that they are stored in the memory, whose addresses are given over here. 3 registers need configuration: the control register, NVIC control register, the NVIC reload register, and NVIC current register. There are 4 initialization steps. So in order to use timer, it needs to be initialized. And by initialization, we mean we are going to set the values of, we are going to update the value of these registers. The first step, step number 1, is to clear the enable bit over here, this bit. We want to clear, meaning we want to set this bit equals to 0 to stop the counter, because the timer, in order to be able to properly configure or reconfigure the timer, it must be first stop. The counter must be brought to halt and stop. That's why we want to set enable bit to 0, because otherwise, there are multiple instructions that are required to be executed in the configuration process, and if we leave the timer ticking, then it might not be properly configured. So better stop it first. Set the enable bit equals to 0. The next step is to set the value of the reload, NVIC reload register. It is essentially, because it's a 24-bit timer, so we're going to use the lower 24 bits, specify the reload value, 24-bit long reload value. So if the reload value is let's say n, some value n, then the timer is going to count down. So the moment it starts running, the next clock cycle, it is going to decrement to n-1, n-2, and so on. So the reload value has been updated in step number 2. After that, by the way, the timer is still in the configuration phase, and it is we haven't allowed it to start ticking yet. Therefore, we proceed to the remainder of the configuration. Step number 3. The current. Clear counter by reading the NVIC current register. Now we are talking about the third register over here. All we have to do is to reset the current value, meaning that we are going to set the current value of the timer. We are going to reset the current value of the timer equals to 0. That means clearing, just as we clear or set bits. So clear stands for setting the current value of the timer equals to 0. And we really want to replace this 0 with the reload value over here. Anyways, the last step, we're going to further configure the timer by setting or clearing bits in the NVIC control register. So back to the first register, because in step number 1 we only set the enable bit equals, we cleared the enable bit. However, clock source, there's a bit clock source. We can run timer at the speed, at the clock speed, which is either the external clock source, external clock, which might be in the form of external oscillator, that occurs when this is equal to 0. For external, to connect a timer clock to the external oscillator, set the speed equals to 0. Or you can set equals to 1, meaning that the timer will now run. So if clock source is equal to 1, it means that timer is going to run at internal clock. So there is an external clock and there is an internal clock. You get to decide which clock is used to run the timer. And that is essentially the speed at which the bus is running. So that's also known as the bus clock or the internal clock. And by the way, I should mention here that you can adjust the frequency of the internal clock by using the phase lock loop, and therefore you can control the frequency at which the internal clock is running or the bus is running. Interrupt enable bit. What about that? The interrupt enable bit. The interrupt enable is used if we want to enable the interrupt on the timer. That is essentially if we want to use interrupt. Because we haven't yet discussed interrupts, so we are going to clear this bit. We do not wish to associate any interrupt signaling with the timer. If we wish to enable interrupt, that would have been useful to interrupt the microcontroller whenever the timer stops running. Enable bit is equal to 1, meaning that we are really asking, we are now setting our timer to run. So as soon as you set this enable bit equals to 1, then it is now allowed to run, and it can now start decrementing. So this is how we configure the timer by setting or clearing the individual bits or we can just load the value of the NVIC control register as appropriate, and also specify the reload value and then clearing the current value of the timer register. Configuring the SysTick timer requires updating the contents of the three registers described in the previous slide. The 4 steps are implemented in the assembly language as shown here. In the first part, we're going to load the address of the NVIC control register into R1, and then we are going to store 0 into register R0, and then store the value 0, which is in register R0, back to the address location containing the NVIC control register. That will automatically clear the enable bit. By setting all of its contents to 0, the enable bit is also cleared. And soon after that, over here, we are going to set the selective bit equal to 1. But after clearing the NVIC control register enable bit, and in fact all the bits have been cleared, we are going to set the reload value. For that, read in the address where the NVIC reload register resides in the memory, put it in an R1, specify the reload value. It's the highest 24-bit number, hex 00FFFFFF. We store this value into R0, and then R0 contents are written back to the address location where the NVIC reload register is placed. So we specify the reload value. Next, we wish to set the current value of the timer equals to 0. We put 0 into R0, and we reference the NVIC current register by storing its address in R1, and then store the value equals to 0, which is in R0, to the NVIC current register. This will clear the counter. So the counter has been reset, the timer has been reset. Its current value is 0. And whenever it starts running, it will start running with the reload value. And finally, we refer back to the NVIC control register, in which we cleared the enable bit. Now it is time to set the enable bit to 1. So enable bit is set equals to 1. That's the least significant bit, you remember. We want no interrupt, and the clock source is also 1. So interrupt is this interrupt. So clock source 1, enable 1, and in turn interrupt enable, or EN, is equal to 0, and all other bits are 0. So that corresponds to, so this setting that enable is 1, clock source is 1, and in turn is 0, this corresponds to the value 5 in the least significant 8 bits. The upper 24 bits are all zeros. So once we have put the value hex 0005 into R0, we store it back to R1. We could have individually reset those bits by using the bit addressing covered in the last lecture. If not, then this is the default way to do it. And then once the timer has been configured, assuming that this is a routine which configures the timer, that initializes the timer, and then whosoever call this routine, we give the control back to the caller. BXLR is the final instruction of this routine by convention. In order to utilize the timer for our application, we need to regularly monitor its countdown status. Bit number 16 of the NVIC control register configuring the timer, therefore, is quite important. Once the timer has counted all the way from its reload value to 0, it sets the count flag. That's when this count bit is set equals to 1, and the timer keeps running. It begins its next iteration starting from its reload value that's specified by this register contents, and the next cycle of the countdown begins. The timer doesn't stop. Whenever the first countdown iteration is complete, the count flag is set to 1, and it stays 1 unless we explicitly have it cleared. What are the ways to clear the count flag? One of the ways is that we write some data to the current register, the NVIC current register, which is holding the current value of the timer. So remember, NVIC current register holds the current value, current count or current count or current value of the timer. Writing anything to this register clears the register so that the NVIC current register is cleared, but it also clears the count flag, meaning that the count is cleared. The other way is that we read the NVIC control register. Whenever the NVIC control register is read, it returns the value, the current value of the count. And once that is read, it clears the count flag. Therefore, we can say that reading the NVIC control register or writing the NVIC current register, both will clear the count flag. Let's look at an example of introducing a delay using the timer. We're assuming that the timer is running at a clock whose frequency is 80 megahertz, which corresponds to the time period 12.5 nanosecond. That is, the timer decrements every 12.5 nanosecond. Now, for example, if we wish our delay to be, let's say, of 125 nanosecond, the question is, what should be the value of the NVIC reload register? So remember, we said earlier that if the value of the NVIC reload register is n, the timer is going to count down all the way from n to 0. It is actually counting modulo n, right? So we want our timer to produce how many ticks? 10 ticks, or 10 counts, 10 countdowns. We want our timer to perform 10 countdowns. And each countdown takes 12.5 nanoseconds, so that will amount to the total delay of 125 nanoseconds. And after that, and then the count should be set equals to 1. So we want our timer to count down 10 ticks before count is set equals to 1. So the value that we are going to put here is equal to 10. So the way to do it is that if the reload value is 10, our timer is going to count from 10 all the way to 0. Now that is not 10, that is actually 11, right? So this value really should be 9. And obviously this is not so consistent, because you think that, well, when 9 multiplied by 12.5 is not going to give you 125. So what we do is that we put the value 10 into register R0, instruction before, and then we decrement the value and then store that value using index addressing to the NVIC reload register. That's the ultimate objective. If you like this way, it is fine. If you want to have the value 9 stored in some other manner, it's also again fine. But the value should be correct. Then we're going to read the current NVIC current register. That essentially is going to so we are going to write to the NVIC current register. That's part of the initiation process. And remember, any value written to the current NVIC current register clears it. So this register, so we are really saying that the timer, so we are really saying that this register is set equals to 0. Even if the value in R node is not equal to 0, still is going to clear. And also clear the count. And finally, we are going to store the address of the NVIC control register. And we are going to keep referring to this address once we enter this part of the code. So once stored, this address will be continuously referred, as I shall describe below. And now we are set up nicely to run our timer. And this code assumes that the other part of the initialization is complete. That is, the routine that we saw before, SysTick init, has been executed, has already been executed. And in case of introducing 125 nanosecond delay, R nodes contain value equals to 10. So these are the things that are assumed before we talk about executing the code described here on this slide. All right, so this is the code segment in which we are going to iterate several times. What it does is that it reads the status of the timer. And where's the status of the timer? It is here. I'm using a different color now. NVIC control register. And within that register, we have quite a few bits, but the one we are interested in is bit number 16, the count flag. That's in which we are interested. And we are going to compare the value of R0 with this hex 00001000. Essentially, we are taking a bitwise AND operation, and we are also allowing the flags to be affected by this AND operation. As a consequence, if R0 is all 0, this is going to set the 0 flag. And if the 0 flag is set equals to 1, which essentially means that the count is 0. Meaning that the 16-bit, the count flag, as long as it is 0, R0 contains 0 and the 0 flag is equal to 1. The next instruction, it looks at the 0 flag, branch if equal. If that is set, and this is true as long as the 0 flag is 1, which is when count is equal to 0. Go back to the instruction whose label is SysTick wait loop. Again, read the status. Again, compare using, well, it's not comparison, it is a bitwise AND, but it works the same way. And so we keep on monitoring the status of the count flag. As long as the count flag is equal to 0, we keep looping. We keep looping. Essentially, microcontroller is just, doing nothing. It is just iterating between these three instructions. It's not doing any productive task. So the moment the timer has counted all the way from 9 to 0, that is when the 10 number of ticks are complete. When the 10 number of ticks are complete, the count flag is set equals to 1, and then this instruction will not be executed. And we exit. So this will not be executed, and we come down over here and exit the routine. So this occurs when Z flag is equal to 0, count is equal to 1, and R0 value is hex 0001000. That's when we are going to exit this routine. And the delay has been completed. Note that we have just developed a routine, SysTick_wait, that introduces a delay R0 times 12.5 nanoseconds. And in that process, the register R0 has inevitably become an input to this routine. Now let us look at a more complex example in which our delay composed of two numbers. In fact, it is a product of two numbers, one coming from the register R0 and the other is a constant 10. The product of two number times the millisecond, that is the total delay we are interested in introducing. And this example also assumes 80 megahertz clock. Now our main objective of implementing this routine is to utilize the one that we have already written, that was the SysTick wait routine. And remember, the SysTick wait routine introduced a delay. It introduced a delay corresponding to the counts R0 number of clock cycles or ticks. R0 clock cycles, a delay corresponding to R0 clock cycles ticks, and in terms of time, it was R0 times 12.5 nanoseconds. So that was the delay. So this SysTick_wait routine introduced a delay R0 times 12.5 nanoseconds. So the routine assumes that the input is in R0, that is the number of clock cycles that for which we have to wait, and each clock cycle is obviously 12.5. So nothing has changed from the last program, except just that our delay now composed of two numbers, a product of two numbers. So the important thing to note is that because we are going to invoke this routine, we first need to store its value somewhere in the register R4. So value of register R0 will be stored in a register R4. So now we systematically try to understand the program, noting that the prefactor, although is contained in R0, but because R0 is also going to be used later when we call the routine SysTick_wait that we developed before, therefore it is important to first save the value of R0 in some other register R4. So the prefactor is technically in R4. Now, if we want this whole program to be called by some other program, like we do very often in case of modular programming, then we also don't want our R4 value to be changed. Therefore, it will be much safer if we first push the value of R4 onto the stack. And because we are going to call a subroutine SysTick_waits, and that is going to modify the value of the link register. So because of this subroutine, so this routine, imagine this is a routine, and this is a subroutine. That is a routine that is called within a routine. So we're going to store the value of link register. That's what we do. That's what we have seen in the previous lectures when we talked about the addressing modes in the stack. All right, so once the value of R4 has been saved on the top of the stack, now we are going to store the value of R0 into R4. So that's this guy, R0 is stored in R4. And we're going to check if we are saying that if R4 is equal to 0, meaning R0 equals to 0, then we are done. Do not introduce any delay. Pop the value of R4 and pop the value of link register into the PC and return to the caller. Return to the caller. So go back from where we actually invoke this routine. That's what we mean by return to the caller. So whosoever called this routine, return to the instruction after that. If that is not the case, this BEQ is false, that is R4 is not equal to 0, then go to the next instruction. Okay, so the next instruction, label SysTick wait 10 milliseconds loop, and you're expected to loop in this part of the code quite a lot, and let us try to understand how this happens. We're going to load the address of delay 10 millisecond constant that is stored as part of the code, that is 800,000. So this 800,000 is used, that corresponds to 10 milliseconds. So if you allow timer to count from 800,000 all the way to 0, then it corresponds to the 10 milliseconds delay. So set the value of R0 equals to 800,000, that is actually 800,000, and invoke the routine. That is going to introduce a delay 10 milliseconds that we've seen before. And then once you return from that routine, subtract the value of R4. So remember, R4 corresponds to this prefactor, that is actually R0. So remember, this prefactor R0 is going to be contained in R4 all the time. It's going to be contained in R4, and we decrement. And as long as R4 is greater than 0, that's the conditional branch higher than. So as long as R4 is greater than 0, and the flags for this branch were set by this sub instruction. The sub instruction is going to subtract 1 from R4 and see if the answer is greater than 0. If that is so, we are going to loop. We're going to go back to this instruction. We are going to load the delay amount, wait for another 10 milliseconds, and once return, decrement R4. So this will continue again and again and again, unless the time when we get R4 equals to 0. That's when we exit this loop and proceed to the end of the routine, that is return to the caller. With that, I would like to conclude a lengthy lecture. I hope you enjoyed listening to this lecture, and you may have some questions in your mind. For that, we are going to have our regular Q&A session on Thursday afternoon. But before I sign off, I would like to give slides credit to Jonathan Volveno. These slides have been taken and modified and tailored to the needs of our Mechatronics Embedded System course. Thank you very much and have a nice day.